All right, well, it's not every day that we get to talk about one of the most important ideas about derivatives. But today is one of those days because we're going to be talking about the chain rule. Cha-cha-cha-chain rule, talk about chain rule, do the chain rule. Yeah, it's a wonderful idea. Now, if you're not familiar with what the chain rule is, well, we're going to change that. And what is it about? Well, it's about what happens when you have a function. And a function, of course, we can go as deep as we want. A function within a function within a function within a function. It's kind of like Inception, a dream within a dream within a... same ideas, right? Just layers upon layers. All right, well, let's dig in. So the basic picture we have is the following. You can think of you have a series of functions. And what's happening is you start by plugging something in to your first function, and out comes the output, g of x. And you say, hey, plug that right into your next function. And out comes the output, f of g of x. So that's what we mean when we talk about, a function within a function, or a series of functions. So we're doing a sequence of evaluations where the output for one immediately goes into the input for the other. And now the question is, well, what happens if I perturb x? So if I change x a little bit, well, that will cause the output g of x to change a little bit. But now what's going to happen is g of x, that has changed in that value, and so that's going to cause the output here to also change even more in some sense. So now the question is, okay, how do we handle the effect of the function in the first layer? So in our case, the g, and the effect of the function in the second layer, f, to see what the total effect would be to the change in our function f of g of x. And the answer is so beautiful. It's that the derivative of f of g of x is f prime g of x times g prime of x. Now, one way you can think about what's happening here is if you think about what is g prime of x talking about. Well, g prime of x is the change that would come from the first layer. So it says, hey, I've changed my input. The net change is measured by the derivative because the derivative is talking about how change is happening. Now, where's the other term coming from? Well, the f prime g of x is actually the same idea. It says, now come to your next layer and say, okay, I want to understand that change. And here's the idea. I need to understand the change based upon what my input is. See, g of x is what's coming in. So it's the rate of change where my input is g of x. And so the moral is, when you have things nested, a function within a function, you're multiplying the pieces together. So it's sort of like if you have go to a sale and you're like, well, there's a manufacturer coupon for 10% off, but today is a special day where you have another 20% off. Well, how do you figure out how much is actually off? Well, you multiply the results together, and that's how you figure out what the new price is. You don't add, you multiply. Okay, so let's just do a quick sketch of the proof, because every rule that we have for derivatives comes from saying, all right, let's actually look and see what the limit says. So if I want to look at the derivative of f of g of x, that's the limit as h goes to 0, f of g of x plus h minus f of g of x, right? Because I take this expression, replace x by x plus h, minus the expression all over h. Well, now we're going to choose a well-chosen one. You see, what we've done at the next stage is we've multiplied where we have a g of x plus h minus g of x upstairs, a g of x plus h minus g of x downstairs, and we say, hey, those would cancel out and give us 1. Now, the second half, it's pretty straightforward to see that this is the definition of what g prime of x is. G of x plus h minus g of x all over h. What about the first piece? Well, what is this? Well, we have to think about it a little bit. The claim is it's f prime of g of x. And how do we think of it? Well, if we think about what's happening here, in fact, here's the outline. we'll say, let's let this g of x, we'll call it a. And we're allowed to change the name of things to make it convenient. And b is g of x plus h. Then as h goes to 0, b goes to a. Okay, that seems reasonable. So what you have is f of b minus f of a over b minus a. Ah, that's the derivative of a. But now we say, hey, the derivative of a is g of x. And we're done. Except, of course, there's a tiny little detail, which you'll notice I didn't say this is the proof. I said this is the sketch of the proof. But we're going to be satisfied with this because what's the small missing detail you have to be careful of? The small missing detail you have to be careful of, how do we know that this isn't 0? That's a good question. I mean, we don't know it's not 0. Now, most times it's not going to be 0 because it's going to be roughly corresponding to our change. Now, it could be the case that it is 0 if, for instance, we're at a place where the derivative of g is 0. And how do we fix it? How do we patch it? Well, we do a little bit of case analysis and say, well, if this were 0, then this whole expression would be 0 anyways, and therefore it's equivalent to what would happen. There's some annoying details to work out, and we're not going to worry about them. Just say we know that they have been worked out. All right, so there we go. That's the chain rule, and it's so wonderful. It's just, it's so elegant, you know. There's not some weird mysticism going on. It's just saying, hey, if I have a function inside a function, I look at the change at both of them at all the levels, and I multiply them together, and there you go. All right, and so we have a couple of notes here. So this is really a few notes. First off, why do we call it a chain? Well, one time, I should say one notation that you sometimes see when you have functions within functions within functions. So if you have f of g of h of kappa of x, well, sometimes you'll see it written with a circle as the composition. And it looks like it can form a chain. So f circle g circle h circle kappa really is just a way of saying f of g of h of kappa of, you know. So I think this is one of the reasons it's called the chain rule. Okay, so what's our procedure? Well, we differentiate the outside function, plug the inside function into that derivative, and I think this is the part where if people struggle with the chain rule, it might be they forget, oh, right, I need to leave the inside alone. That needs to stay by the way it was. And then multiplying the outside by the derivative of the inside, right? So what does this say? So if I have the derivative of f of g of x, so the outside function is f, so take the derivative, then whatever was being plugged in still goes in. So that's g of x. Then multiply on the outside by the derivative of the inside. So g of x is g prime of x. Now, of course, this is a function in a function, but we can have multiple layers, many layers. So it's like an onion. And sometimes I like to call these onion problems because onions have layers. And also, if you do some of these problems, it might bring us to tears. Tears of joy of getting to do calculus. So what do? The answer is work one layer at a time. So suppose we try this. So suppose I ask the question, what's the derivative? And I'll still say stay symbolic right now. So of f of g of h of x, right? So what do? Start with the outside. So we're going to take derivatives outside in. Derivative of f, we denote that by f prime. Now, plug the inside into there. So that's g of h of x. Now, next, I multiply by the derivative of the inside. Well, here, it's a chain rule. So the derivative of g is g prime, but plug the inside in. So h of x times by the derivative of the inside. Well, okay, what's the derivative of the inside? Well, that's going to be h prime of x. All right, and you could say, all right, can we keep going? Well, you could. What's the inside? It's x. And what's the derivative of x? Is 1. And so you're done. By the way, let's just do a little fun side note, right? Okay, so sometimes we talk about, the derivative of e to the 100, what is that? Well, it's 0, right, because it's a constant. But of course, a lot of students not paying attention will say, it's e to the 100, right? Because the derivative of e to the x is e to the x. So you're like, well, if I see e to anything, I should say, but the derivative of that is e to anything. And, okay, well, what could we say? Is it e to the 100? Well, you could actually say it's e to the 100 if you think of the outside function as being e, the inside function as being 100. But, so you take the derivative of the outside, plug the inside in, and now what do you need to do next? Now you multiply by the derivative of the inside, and the derivative of the inside is 0. So you can apply the chain rule to take a derivative like e to the 100 and say, well, yeah, it is e to the 100 times 0, and the net result is that it is 0. Now, there's a lot of special cases of the chain rule, and probably the one you might encounter most often out in the wild, if you're walking around the street and say, I recognize that. That's a really special case of the chain rule. It's called the general power rule. And that says, suppose you have the derivative of a function raised to the power k. So some function raised to the kth power. Then the rule says it's k, that function raised to the power k minus 1, times f prime of x. Now, how does that rule work? Well, what's happening is you have, in fact here, this is a function. Let me move it up a little bit here. This is really g of f of x, where g of x is called x to the k. All right? Because what does this function say? It says whatever you plug in, raise it to the kth power. So if you plug in f of x, you get f of x to the kth power. Now, what is your g prime of x? The derivative of x to the k would be k x to the k minus 1. So according to the chain rule, it says take the derivative of the outside. Here's my derivative. Here's my function of the outside. Here's the derivative of the outside. Plug the inside in. So it'd be k f of x to the k minus 1. So that's where that piece is coming from, times the derivative of the inside, which is f prime of x. You can make a whole bunch of these rules. You can say, well, what does the derivative of e to the f of x look like? All right, we could just write that one down. We don't even have to put a lot of thought into it. So the derivative of e to the f of x, well, what's our inside? What's our outside? The inside is f of x. The outside function is e to the x. It's e to the something. So taking the derivative of the outside, derivative of e to something is e to something. So plug the inside back in. So that's e of f of x times by the derivative of the inside. So times by f prime of x. So that's where we got this derivative of e to the 100 is 0. And again, you can make more of these rules. But generally speaking, I think the general power rule is one that is most likely to be used. It's a very nice rule. One more idea, and there's this notation for chain rule, and we call this Leibniz style. Now, if you haven't encountered Leibniz's name, he was another mathematician, a contemporary of Newton, and depending upon what country you grew up in, you may not have celebrated Newton, you may have celebrated Leibniz, because they both came up with calculus at more or less about the same time. And he had better notation. And so we'll say, all right, how do we think about the chain rule? Well, again, what we'll think of is we'll think of a function, f of g of h of x. But what we'll do is we'll introduce some new variables. So we're going to call each level a new variable. So our innermost level, we'll give that a variable. Let's call it v. So v is h of x. So then our next level up would be g of our new variable v. So we'll call that u. U is g of v. Then g of v, next level up, well, that would be f of our variable u, f of u. So what do we have? Well, what we have is the following. We have a series of variables now. So y, u, v, x, such that really, what do I have? Y, it depends on u. U depends on v. V depends on x. So the diagram here is showing us the interrelationships between our different variables. And now, what do? Well, suppose I want to ask the question, I know x is changing. What's the effect up here? How does the change in x affect the change in y? All right, well, we got to think about it. How do we get from x up to y? And the answer is we sort of have to work our way up one level at a time. So what we can say is, well, x it's affecting how v changes, and then how v changes affects how u changes, and how u changes affects how y changes. And so we have the following. If I want to know, dy dx, well, I can say it's the product of dy du, du dv, dv dx. So how much does y change with respect to u? How much does u change with respect to v? How much does v change with respect to x? Now, at first glance, when you look at this, you're going to say, well, of course it is, right? Because what do you want to do? Well, you want to look at this kind of expression. I'm going to make a little note here to the side, just recopying. And you're just tempted to say the following. It's like, well, yeah, look, the du's cancel, the dv's cancel, and what's left is a dy over dx. And you're like, okay, so yeah, it equals dy dx. Life is good. We can move on. Woohoo, good. Calculus makes sense. Except for one small detail. Dy over dx does not represent, here's this little thing called dy, and here's this other little thing called dx, and we're dividing. See, dy dx is one single thing. It's one notational thing. So I don't have that this dy and that du are separate objects. So I can't cancel this du with that du. So there's a little bit more subtlety, but not much. And the thing is, if it helps you remember, then go with it. Go with it. Because at the end of the day, there is this sort of idea going on. Indeed, if you go back to the way that the proof worked, you can think of that limit, right? We had that f of g of x plus h. Well, let's just pull it back, right? See here? There was like, here's our change in y, and here's our change in u. Here's our change in u, here's our change in x. And the idea was, look, ultimately, these would end up canceling. So that we were really, in some sense, replicating this philosophy when we did the sketch of our proof. All right. So anyways, that's the chain rule. Very important rule. And I would say, the reason I say it's a very important rule is that a lot of the functions are described in this manner of putting functions into functions into functions. And so that it's a very natural process. In some sense, we oftentimes describe the behavior of things sequentially. First, you do this to your expression, then you do that to your expression, then you do that to your expression. See, every time you're doing that, what you're doing is you're saying, here's layers within layers within layers of instruction. And so the chain rule helps you unravel what the effect is. And it's, again, very important rule, which means you're going to see it a lot, so you need to get lots of practice with it. You'll see it a lot in the practice today, of course, obviously, but also a lot in the future. All right. Well, that's the idea. Let's get practicing.